All right, this should be a pretty quick video, I hope. We're just going to go down all of the linear terms that we've learned this year and compare them to the rotational terms that have come up in this unit. Starting with the variables, I have this x variable, and in rotational terms, it is theta. So we talk about the linear distance versus the angular displacement. Then the change in theta over time is the angular velocity, omega. The change in omega over time is the angular acceleration, alpha. Time is the only term that is the same in both rotational and linear terms. Then mass is the rotational inertia that we've talked about a lot this week. Force becomes torque. Linear kinetic energy or translational kinetic energy has a rotational version, rotational kinetic energy. And then linear momentum is capital L, or angular momentum, in rotational units. So going down the units real fast, we have meters for position, meters per second per second, seconds, mass is in kilograms, force is in newtons, sorry guys, then we have joules, and finally we have momentum is in kilogram meters per second. In rotational terms, the units of theta are in radians. Then we have radians per second per second, just seconds. Then we have kilogram meters squared. We have Newton meters. This is still in joules. And then this one is kilogram meter squared per second. Yeah. Cool. So going down this list, you should hopefully see that there's some strong similarities. For example, a radius times a meter just gives us those units. So, or sorry, if we multiply that by the radius, that gives us the angular term. Again, multiplying by radius gives us that term. Again, multiplying by radius gives us that term. We don't do anything here because they're the same variable. This one here, though, we're kind of multiplying by radius squared and that other constant that shows up in the table. This one we're multiplying by r. This one we don't do anything with. And then the last one, again, we multiply by the radius. So there is some quick and easy ways to convert between linear and angular terms using these. And then, so there it is. Hopefully this will help you keep track of our variables and our units. Last thing that I'm going to do is translate all of our linear formulas into rotational terms. And really what you're just going to see is I'm going to be replacing these variables with these variables. So going down the list, we have omega equals omega naught plus fish acceleration times t. We have theta equals theta naught plus omega naught t plus 1/2 fish acceleration t squared. Velocity squared equals velocity naught squared plus 2 fish acceleration times delta angular displacement. Angular acceleration is equal to the sum of the torques over the rotational inertia. The kinetic energy in rotational terms, instead of being 1/2 mv squared, is 1/2 I omega squared. I just replaced the m with I and the v with omega. Linear momentum is mv. Angular momentum is I omega. Again, I just replaced the m and the v. And then for the angular impulse, or the change in angular momentum, that's delta L, I replace F with torque, and I keep delta T the same. This is kind of a weird looking one because it has like 2 different T's in the same formula. So just be aware of that. And we will talk more about this stuff. We haven't really gotten to them yet, but I didn't want to do another video that just does this comparison after this. So those are all of the formulas and all of the variables and all of the units for this entire unit, if it helps you kind of do a quick review and see everything together. So thanks for watching. Have a great night.